Good afternoon, everybody, or maybe good morning for some of you. It's my pleasure to welcome you to this journal webinar. Today, we will be discussing the paper Visualizing the Effects of Predictor Variables in Black Box Supervised Learning Models by Daniel Apley. The paper was published in the Journal of the Royal Statistical Society, Series B in 2020, and it has been selected by the Royal Statistical Society Webinar Scientific Committee due to its impact and relevance. Daniel's presentation will be followed by a discussion given by Gilles Hooker from the University of Pennsylvania and King Yuan Zhao from the University of Cambridge. And after the discussion, there might be a rejoinder and there is time for open discussion. So if you have any question or comment, please feel free to write them in the chat or to tell them aloud during the open discussion session. The webinar will be recorded and it will be published on YouTube. So if someone doesn't want to be in the movie, please write the Royal Statistical Society and the video will be edited accordingly. Please keep also your microphones muted during the presentation. And yeah, I think that's it. So it's my pleasure to call on Daniel to present the paper.
Okay, well, thank you, Angela, and thanks to Qing Yuan and Giles for being discussants, and thanks to JRSS for inviting me to do this. This was joint work with my soon-to-be former PhD student, Jingyu Zhu. The setting is you've got a set of data, you've fit a supervised learning model to it. X is the vector of the inputs to the model. F of X is basically just what the model spits out as the predictions. I could have put a hat over it because it's really fit to data, but to clean up notation, just F of X with no hat represents your fitted model. And then again, you fit it to a set of supervised learning training data that's got a response Y and a vector of predictors. D is the number of predictors, N is the number of training observations. If you want to think statistically, what you're trying to estimate when f of X in a regression problem is the conditional mean of Y given your predictors, or in a classification problem, it'd be the probability that Y falls into one of the classes given the predictors. If it's linear logistic regression, you don't need any of this. They're very interpretable because each predictor's got a coefficient and the effects are linear, so you know exactly how the X's affect the predictions. All the other models, though, it's not the case. All the popular models that people use now, tree-based models like random forests, neural networks, support vector machines, and so on, they're all black box in the sense that you can't look at it, all the many parameters of the fitted model, and understand the effect of the predictors. So what the goal here is just develop a tool that applies to any black box supervised learning model that will help you understand what the effect of the individual predictors are on the response. And that includes which predictors have the biggest effect on the response, what is the nature of their effect, if you increase the predictor, does it increase or decrease the predictions, is it monotonic, is it linear, how nonlinear is it? Let me illustrate what the goal is and what this produces with an example. And this is the same example we used in the paper. This was bike sharing data from a bike sharing rental system in Washington, D.C., collected over a 2-year period. This is publicly available data. About 18,000 rows of data. Each row represents 1 hour of bike rental demand. The response is the number of bike rentals in that hour. There were 11 predictors, 8 were numerical. Month of the year, there was 12 months, hour of the day, 0 through 23, day of the week, weather situation. That was measured too on a scale of 1 to 4, larger being worse weather like rainy or hail or snow. Temperature in degrees Celsius, something called A-temp, which is sort of a feeling temperature, a heat index or wind chill factor, humidity and wind speed. And then there were 3 categorical predictors. The year, which we treated as categorical because there was 2 years, whether or not it was a holiday, and whether or not it was a working day. If it's a weekend or holiday, it's not a working day. Otherwise, it is. So to this data set, we fit a neural network using neural net package in R. It had tuned it via cross-validation. It had pretty good cross-validation R squared of 90%. So it captured the predictive relationship. Question is, how do you interpret the model? How do the different predictors affect the response? These are examples of ALEPlots, main effect ALEPlots, that show the effect of individual predictor variables with the other predictors averaged out in a sense that I'll talk about shortly. So the four predictors I've created ALEPlots for here. The vertical axis is really the predicted response, suitably averaged in the sense I'll describe shortly. You average out the other variables. So this shows you can think of as the main effect of month of the year on the bike rentals. In January, February, it's low. It sort of slowly increases and peaks in September and October and then drops back down. Same plot, but for the other predictor that's hour of day, 0 is midnight. So you see not many rentals in the wee hours of the morning. And then you got a morning rush hour peak. Then it drops down for the mid-afternoon lull. And then you got an evening rush hour peak where rentals increase. Weather situation, again, 4 is worse weather, 1's better weather. As the weather situation worsens, the rentals decrease monotonically, and same thing for the wind speed. So looking at plots like these help you understand the effects of the variables. Doesn't tell the whole story. These are just main effect plots. Oftentimes in models like these, pairs of variables will have interactions with each other. We've also got, ignore the left plot. The right plot is a second order AL interaction plot showing the joint effect, combined effect of two predictors. In this case, hour of the day and then weather situation, which tells a somewhat similar story as the main effect plots, but a little bit different. If you look at good weather situation in one and go across horizontally, the values on the contours are, again, the predicted response from the model with the other predictors averaged out. For good weather situation, the rush hour peaks, morning and afternoon, are actually much more pronounced than what they appear on the main effect plot. And then likewise for bad weather, the rush hour peaks are still there, but they're much less pronounced. So looking at the interaction plots too are important if you've got interactions. That's sort of a preview of what this method produces, plots like this. Most of the rest of the presentation will be explaining what they are exactly. But first, why do you care? Why is this an important problem? What initially got me working on this problem was that we've got a master's in analytics program. All the students, teams have practicum and capstone projects. Every project I work on, you fit a supervised learning model and go to discuss it with the client. And first question they ask is, well, explain the model. Which predictors are important? How do they affect the response? And I realized the existing methods were not perfect, so I started working on this. In general, why do you fit supervised learning models? Well, usually either for predictive purposes or explanatory purposes. If the purpose is explanatory, it's obvious why you care about predicting the response. But even if it's just pure predictive purposes, understanding the model is important for transparency, to sanity check, to make sure your model is trustworthy. Sometimes you have to in regulatory environments. A lot of times you fit a model like this, you think you've got good data in a good model, but you fit the model and then something violates intuition. Like if it's a healthcare study and the response is the risk of heart disease and a predictor is the age of the patient. You fit a model and you think it's tuned well and good predictive power, but you see something like this where heart disease risk goes down as the patient's age increases, you've probably got a bad data set. Or you've discovered something really surprising and interesting. But either way, you want to know about it. So that's why this is important. Why is it challenging? If you want to understand the main effect and interaction effects of pairs of predictors on the predictions, you have to do some type of averaging across the other predictors. Notation I'll use throughout here, if you see X with a \J, it means all the predictors except the jth one. So you got to average across the other predictors somehow. If all your predictors were independent magically, then it's actually pretty easy to do and straightforward, but that's usually not the case with observational data sets. You almost always get some predictors that are pretty highly correlated. All right, let me just talk about some existing methods. By far, the most common existing approach was partial dependence plots that I believe were first developed by Jerry Friedman in the gradient boosted machine paper, but they apply generally to other black box supervised learning models. There's something that's sometimes called marginal plots. It's not a great name for it. I think I got this from the hasty Tibshirani-Friedman machine learning book, so I'm using the same terminology. Marginal plots really are never used or shouldn't be used for reasons I'll discuss next slide. So partial dependence plots, sort of the state-of-the-art existing methods. There's something called conditioning plots or conditional response plots and conditional expectation response. They're a bit different. What they essentially do is they plot your predictions. Again, F is the prediction spit out by the model. They plot it as a function of individual variables for fixed values of the other variables. So these really produce a collection of plots, and it can be thousands of plots in the same plot. So they get kind of messy, and they're also subject to the same extrapolation problem that's the main problem behind partial dependence plots. There's also something called functional ANOVA. Sobel decomposition was, I guess, the original version of that. Giles had a really nice paper in 2007 that extended it to dependent correlated predictors. They've got pretty interesting theoretical properties, but as far as I know, they're not really used for understanding, visualizing the effects of variables in supervised learning models fit to big observational data sets, primarily because they're really, really computationally expensive. So partial dependence plots and marginal plots. This kind of sets up the motivation for ALEPlots. This is an illustration of what those plots do. I'm illustrating just for the simple case with two predictors, x1 and x2. So here's a scatter plot of a set of training data for the predictors. If you want to compute the marginal plot for x1, that's what the subscript 1 means. It's the plot for x1. What you do is you discretize the x1 axis into, let's say, 50 discrete points. For each of those fixed values of x1, you'd plug that value into your predictive model, and then you'd plug in the random variable x2 and compute the predictions. And you'd average the predictions across the conditional distribution of x2 given x1. So that's what this kind of illustrates. The M plot that you'd plot for x1 equals 0.3, you would plug in all these values of x1, x2 along this line segment, average the predicted response, and that's what you plot. So it's easy to see what the problem with marginal plots are. They conflate the effects of predictors when they're correlated. The M plot value for x1 equals 0.9, you'd plug in these values of x1 and x2 over here. But not only is x1 changed, because of the correlation, x2 is changed on average. So you're also plugging in different values of x2 over here. So M-plots, the big problem is, and why they're never used, they conflate the effects of correlated predictors. Partial dependence plots fix that. And it's the same thing, but instead of plugging in the conditional distribution of x2 given x1, at each value of x1, you plug in random variable x2 using this marginal distribution, basically. Not conditional on x1, but the marginal distribution of x2. So the partial dependence plot value that you'd plot at x1 equals 0.3, you would be plugging in all of the x1, x2 values on this line segment, averaging them, and then repeating for, let's say, 50 discrete values of x1. The main problem with partial dependence plots is what you can kind of guess from this. You have to extrapolate. When you plug in x1, x2 values over in this region, you had no training data that was anywhere close to that. And complex supervised learning models just aren't able to reliably extrapolate typically. So that kind of renders partial dependence plots sometimes unreliable when you got correlated predictors. And then these, of course, are the theoretical definitions. What you compute in practice, given a training data set, is basically just the sample version. Plug in each fixed value of x1, and then you'd go across all n training rows of your data, and you'd plug in the x2 values and average the response over that. Okay, so that's the problem with partial dependence plots. They have to extrapolate. That's the main conceptual problem. And they're also pretty computationally expensive. As we'll see shortly, ALEPlots are orders of magnitude faster to compute. So that's what what the paper was. It was proposing and developing this ALEPlot, accumulated local effect plot approach. This illustrates the basic idea. Again, I'm illustrating for the simple case with just two predictors. If you want to compute the ALEPlot for x1, you would again discretize the x1 axis into 50 discrete points. At each discrete value of x1, instead of doing what m-plots and partial dependence plots do and average the predictions themselves, what you average is the local effect of x1. Local effect defined as the partial derivative of the predictions f with respect to x1. And you would do that for each value of x1. So what you're doing at this point for x1 equals 0.3, you're plugging in x1, x2 values just along this line segment because it's still using the conditional distribution of x2 given x1. So that avoids extrapolation because you're using the conditional distribution and plugging in x1, x2 values here. And then for each x1, x2 value along this line, line segment, you'd compute the local effect of x1, the partial derivative of the predictions with respect to x1. And then this expectation is just averaging a weighted average using this conditional distribution, weighted average of all the local effects of x1 at this point. And then the ALEPlot value that you would plot at each x1 is the integral or the accumulation of all those average local effects from the lowest value of x1 in your training data up to the value that you're plotting at. And this is the theoretical definition that you need for theorems and things like that. The sample version that you compute from your fitted model and your training data is just replacing derivatives with finite differences, replacing expectations with sample averages within bins, and replacing the integral with a summation. All right, so this was just to illustrate the basic idea for a simple case with only two predictors. General definition for general number of predictors, same thing. The ALEPlot for the jth predictor would be you average all of the local effects, the partial derivatives of the predictions with respect to the jth predictor. You average them, plugging in the conditional distribution of all your other predictors, given that value of xj. So averaging the local effects, and then you accumulate it from some smallest value of xj. And you might wonder, well, we got to take the derivative here. What do you do if you've got a tree-based model like a random forest? It's not differentiable. That's completely okay. We've got a more general definition in the paper for non-differentiable. Basically, just replace the derivative with finite differences. And then in the theoretical version, we take the limit of that as the differences, as the bins across which you take the finite differences get smaller and smaller. And then we show that that converges to the same definition when f is differentiable. But the good thing is the estimator, what you compute from data, it doesn't matter if it's differentiable or not, it's still the same estimator that always works with finite differences. So you just take the xj. I think I can illustrate this with a figure better. Ignore all the notation on the right. We probably don't need that. I think I can just explain it with the figure. This shows how you would compute numerical computation of ALEPlot for x1, again for the case where you got two predictors. Here's again a scatter plot of the training data for x1 and x2. The ALEPlot for x1, you would partition the range of x1 training values into bins. We use quantile spaced bins, so there's an equal number of observations in each bin. And then in each bin, if you look at this bin over here, we've got 5 training observations that fell into that bin. For each value of x2 in that bin, you would compute the finite difference in the predictions between the right edge of the bin and the left edge of the bin. So that's the local effect of x1 for this value of x2 in this bin. You do the same thing for all 5 observations, and then you'd average them. Right? That's what the expectation is averaging all the local effects within the bin. And then the ALEPlot that you plot at this value of x1 would just be the summation or the accumulation of the average local effects from your leftmost bin up to the bin that contains the x1 value you're plotting it at. So that's the basic idea, kind of a relatively simple idea. That's just main effects. Again, a lot of supervised learning models. You've got strong interactions between pairs of predictors, and you want to understand those too. Definition of the second order AL interaction plot for a pair of predictors, xj and xl. Same idea. Instead of averaging finite differences or first derivatives, you would average the second derivatives. So take the predicted response f, take its second derivative with respect to the 2 predictors, xj and xl. For the other predictors, you would plug in all their values that occurred conditioned on the xj and xl values, and then you average the second order finite differences, and then now you got a double integrated or double accumulated from the lower left point. And then the convention we used in the paper, we take this function here, the accumulated average second order local effects, and then we subtract, from this function, we compute as main effect ALEPlot values, and we subtract them out from the function. So that's kind of zeroing the interaction. So what you get in the ALEPlot interaction is just the interaction without the main effects included. Then if you want to visualize the effect of both predictors, you can add the main effects back in. Estimator, same logic, just replace the second order partial derivative with a second order finite difference, replace the expectation with an average, and then replace the double sum, the double integral with a double sum, which is what's illustrated on this plot. All right, so this would be how you would compute, given a set of training data, how you compute the second order interaction plot between a pair of predictors xj and xl. Horizontal axis is xj, vertical axis is xl. The bullets are all the training data. You'd partition the xj range into bins, partition the xl range into bins. That gives you a grid of cells. And then for each of these cells, in this one we had 2 training observations. Into your predictive model, you'd plug in the x\JNL, the other predictor values for these 2 points. And then you would plug in the xj, xl values that are on the 4 corners of this grid, and use that to take the second order finite difference. And then you'd average those second order finite differences for all training observations that occurred in this cell. And then the ALEPlot value that you plot here would be the double sum from a lower left point up until this cell. All right, well, that's the basic idea. I probably won't have time in this because it's just a half-hour presentation, but we've got a more general definition of ALEPlots for not just main effects and pairs of predictors, but three predictors, 4 predictors combinations. The software we produce doesn't even calculate those because there's hard to visualize anyway, and we just needed it to show kind of a ANOVA type decomposition theorem. Let me give a couple examples here just to show when partial dependence plots and marginal plots break down. So this is an example with also 2 predictors, just a simple toy example. Here's the training data showing x1 and x2. The predictors are pretty highly correlated. We generated in simulation a response that was linear in x1 and quadratic in x2 with no random error, no noise. For the supervised learning model, we fit a tree to it. A 100-node tree was about the best. Quite a few nodes just because it's noiseless data. So the bigger, more complex tree had better cross-validation error. This little tree schematic here shows the first 8 splits, right? There was 100 nodes, but this shows the first 8. The rectangles here are the partitions corresponding to the first 8 splits. you can kind of see from this why a partial dependence plot might break down. If you're computing the partial dependence plot for x1 at x1 equals 0.3, it has to plug in x1, x2 values all along this line, including way up here. But no training data anywhere here. The predicted response, given the nature of the tree partitions, the predicted response over here is not going to be x1 plus x2 squared, because the model can't extrapolate. It's going to be whatever the predicted response was where you had data over here. So predictions over here, when you extrapolate, are going to be way off. And you can see that in the results here. This shows ALEPlots, partial dependence plots, and marginal plots for both predictors. Left plot are the plots for x1. Right are for x2. The solid lines here are the true functional relationship, which is linear in x1 and then quadratic in x2. Let's see, the marginal plots are the dashed lines, right? And it's no coincidence they're about the same, almost exactly the same for x1 and x2, even though the effective x1 is linear and x2 is quadratic. Marginal plots, for reasons I mentioned earlier, they conflate the effects of two correlated predictors. So that's why M-plots are sort of useless for this purpose when you got correlated predictors, and I don't think used at all hardly for this purpose. The partial dependence plots, that's the dashed red line, they're better. They correctly thought the effect of x1 was linear, or approximately, and x2 was quadratic, but they underestimated the effects of x1 and overestimated the effect of x2. Why? Because of this, you had to extrapolate. That made it unreliable. The ALEPlots, that's the blue lines, they were pretty close. A little bit of noise, but they, for the most part, caught the linear and quadratic relationship exactly. So just a little toy example showing when the other methods break down. Similar example, but this time we fit a neural network and added a little random error to the response data that we fit the model to. And then we did it across 50 replicates just to see how consistent the plots were. So same true relationship, but a different fitted neural network for each replicate. The left plots are the ALEPlots for x1 and x2. The gray lines are the ALEPlots for each replicate. And you can see there's some variability, but for the most part, across all 50 replicates, it was pretty close to the ground truth. Whereas the partial dependence plots just varied incredibly widely and gave totally different results from replicate to replicate because of that extrapolation. It's the same neural network, by the way. The ALEPlots and the partial dependence plots are computed for the exact same model, which was pretty accurate within the training data, but it just wasn't able to extrapolate. So the partial dependence plots broke down. And then how much time do I have? Should I finish up in 5 minutes or? All right,
Yes,
well, let
yes,
me
5 minutes is okay. Sorry.
All right, 5 minutes, I'll finish. I usually give an hour presentation. I got a lot of other stuff in here, which I won't have time to cover. So let me just go back to that bike sharing example because it produced some interesting things. Guess I've already showed the AL main effects and interaction effects for some variables, which all seem to make sense. You got the rush hour peaks and weather situation worsens or wind speed picks up, rentals go down. And then the interaction plot showed that, well, the effective hour of day wasn't just the effective hour of day. It depends on what the weather situation is because of the nature of the interactions. There were some other interesting things. Yeah, for feeling temperature, that was like the heat index / wind chill variable. That's highly correlated with temperature, of course. I should point this out. For most of the variables, ALEPlots and partial dependence plots were very close. It's just for some variables, in some examples I've encountered, you get substantial differences. And when that almost always is, or maybe always is when you've got highly correlated predictors and the model's not able to extrapolate. Here's one variable that had very different ALEPlots versus partial dependence plots. This was the main effect of feeling temperature. Left plot's ALEPlot, right plot's partial dependence plot. Let's see, degrees Celsius. So and both ALEPlot and partial dependence plot are interpreting the exact same fitted neural network, which had cross-validation R-squared of 90%. So a pretty accurate model within the training data, but evidently not able to extrapolate. The ALEPlot, when it interpreted the model, thought there was an optimum biking temperature. If the temperature's, let's see, this is about 74, 75 degrees Celsius for the heat index. If it was much colder than that, people don't want to bike as much. If it was much warmer than that, people don't want to bike as much. The partial dependence plot missed that and thought the effective feeling temperature was monotonic. So you probably can't interpret these plots way over here. That corresponds to like a heat index of 120 degrees. I don't think they had any data for that. But this is Washington, D.C. in the summer, so they had some heat indexes that were around 40 Celsius. So probably about up to here is all you can interpret the plots at. But either way, the partial dependence plot thought that when the feeling temperature went from 75 Celsius to 100 Celsius, rentals increase. Which is right? Who knows? We don't know the ground truth. This is real data, but I think the ALEPlots make more sense. And given that they behave better with extrapolation, I'm guessing the ALEPlot was more correct. And I should point this out. Huge difference in computational expense. ALEPlots took less than 1 second for each AL main effect and interaction plot. It's the same for the main effect and interaction plots, roughly. Partial dependence plots took 25 seconds for each main effect and about 8 minutes for each interaction plot. I used k equals 100 bins. I could have used smaller and reduced expense, but it's still, for interaction plots, partial dependence plots are usually very expensive with big data sets. And then let me just last slide here. This is something that is not in the paper, a variable importance measure, kind of based on ALEPlot concepts, just to take each of your predictors and just attach a numerical score to it that measures how important it was, considering both its main effect and all order interactions, kind of like used for the same purpose as Shapley effects or permutation-based variable importance, but a alternative to that same PhD student, Jing Yu, that I did this work on, she just finished her PhD thesis, and we're about to submit a paper on that. I won't have time to explain what they are, but this just shows the results for the variable importance measures. We've got both a main effect variable importance measure and a total effect that includes interactions of all order. If you ignore the top plots, the right plots, the bottom plots, the right one is the total variable importance measure, a Pareto chart ordered in terms of which predictors were most important. Hour of day had the largest variable importance. And these are in units of variance, by the way. I probably should have taken the standard deviation and plotted that, in which case the difference between the most important and the second most important wouldn't have looked quite so extreme. But hour of day was the most important. Whether it was a work day was next most, and then year and so on. What's interesting here, if you look at the second most important variable, workday, if you look at its main effect importance, this plot, it had no main effect importance, and yet it was the second most important variable. That tells you one thing, that it must have strong interactions with some other variables. So next thing we did was we looked at second order interaction ALEPlots between working day and the other predictors to see which one it interacted with. The two that it interacted the most with were hour of day and temperature, both of which are kind of interesting. This is the second order interaction plot. The contour values are, again, the predicted response. Oh, we also added the main effects, AL main effects. We added them to the interaction effect. So this shows kind of the combined effect of these two variables. I guess the only thing that's relevant to look at here are if you look at the contour plots along these two vertical lines at working day equals 1 and 2. 2 means it's a working day, 1 means it's not. The effect of hour of day is totally different, which is kind of obvious when you think about it. If it's a working day, you get the morning rush hour peak, you get the afternoon rush hour peak, you get the mid-afternoon lull. That completely disappears if it's not a working day. which again is obvious when you think about it, but sometimes seeing these helps bring out obvious things that you might have missed otherwise. So this kind of speaks to the point again that if you just look at the main effect plot for hour of day, you miss a lot because the effective hour of day depends strongly on the other predictors. And then same thing, the interaction plot between temperature and working day, that was kind of interesting too. Whether or not it's a working day, the effect is sort of the similar conceptually. You've got an optimum biking temperature right about here, but the rate at which the rentals decline when the temperature deviates from the optimum is a bit different. If it's not a working day over here, if it's not optimum biking temperature, rentals drop down more quickly than if it is a working day, which I guess makes sense. If it's a working day, probably you got a lot of work commuters who rent bikes to get to work. Maybe it's their routine, and if the weather's not optimum, they're still more likely to rent a bike. Whereas if it's not a working day, maybe most of the bike rentals are vacationers going around to museums in DC, and if it's not comfortable biking weather, they tend not to rent bikes more. And I think that's probably about all I can talk about here. Yeah, the other, when I have a longer presentation, I also talk about some theoretical properties, consistency of the estimators and things like that, but I don't think that's no time to do that. So I'll stop here and thank you again for your attention.
Thank you, Daniel. Sorry for shortening your presentation, but we have time constraints, of course. Thank you very much.
Yep,
so now let's move to the discussion. And I am pleased to call on Gilles Hooker from the University of Pennsylvania.
First of all, I want to thank and congratulate Daniel and his student on both a very nice presentation, but really, really very nice work. I'll try and keep this relatively short. I'm going to try and put a little bit bones on, well, what is it that's happening to extrapolation when things go bad? And then ask some sort of more general questions about trying to understand what ALEPlots really do. And I'm going to restate this sort of statement a little bit more explicitly in terms of asking about, avoiding omitted variable bias. By saying, if I can be a little more specific about the point, and I appreciate that this is maybe not what the authors originally intended. Interventional feature attributions interventional has been a term that's started to be used within the explainable artificial intelligence literature to say these are feature attributions in which you deliberately break a relationship between xj and x minus j. And they call it interventional because there is some analogy to a causal effect in which you can, directly manipulate the feature that you're interested in looking at. And part of the justification is also that these recover sensible values if the model is globally additive. And that's basically at this point nearly a requirement. That is, if you have an additive model, your feature, your summary about that feature should be the summary that you would have if you just gave it the additive component that corresponds to that feature. But as Dan already demonstrated, this can require a lot of extrapolation to make work, and that means that, in fact, that reduces the salience of this kind of global requirement of additivity. And as we've pointed out, things like mPlots borrow signal, so you get omitted variable biases, and these ALEPlots really manage to capture the shape of these additive components without requiring extrapolation. So just to come back to some of this, and I'm really pleased to see this being picked up because I've yelled about extrapolation for a long time into the winds. This is just a little picture from many, many, many years ago. It's actually from my PhD thesis. I mocked up this nominal feature distribution, having seen exactly this kind of a pattern in the Boston housing data. In which we have the red points are my original data points, and the blue points are all the places you would evaluate your model if you're trying to produce, in this case, partial dependence plot, or some of the feature importance metrics. So in addition to partial dependence plots, similar ideas were developed by Leo Breiman to look at asking about how important is a feature, and it involved permuting the value of x1 relative to x2 and asking how much that hurt your ability to predict. So what happens when you try and extrapolate? So here's a little story. I probably got approximately the same kind of generative model as Dan did in generating these features. This is a paper I wrote in high dudgeon when I saw people still using these sorts of tools. These are correlated x1 and x2. A model is just that f is equal to x1, so I ought to have nice vertical contour lines. And what you're getting is that these contour lines really bend over when you're using a neural network. And I've plotted the splits that the first 10 trees in this is, sorry, a random forest. I've plotted the splits that the first 10 trees in the random forest make on these two features, and you can see that a lot of the time they're splitting vertically, which is what you want, but some of the time you're reaching over indeed from the other side. And it's something like saying I am, in fact, when I'm extrapolating, doing approximately marginal regressions on each in order to get to this kind of attenuation here. What that means is that even if I say there is some sort of additive model going on where I have data, most machine learning functions aren't going to extrapolate like their additive models. So saying I'm going to, in an interventional sense, recover additive components is problematic. Neural networks do something similar, something different, and we saw that in some of Dan's plots as well. Just to recapture that, here's the same data set. What the neural networks are doing is basically shoving a lot of their degrees of freedom outside of where you have regions of data. And that means that they basically exhibit very high variance. This is the variance between 100 simulated neural networks on now different responses in the data set. And it really explodes outside of the range of the data. The effect, and the reason I was in high dudgeon, was actually about variable importances, which wasn't really which wasn't what ALEplots were intended to produce. But if you ask to screen about, say, which variables matter a lot, and you use a permutation-based importance metrics, so producing this sort of extrapolation, as you increase the correlation between two variables, you actually tend to increase their overall importance relative to others that effectively we've set this up to look at relative to features that otherwise have marginally the same kind of impact on the model. And that turns out to be really hard, to get rid of, even when you've got fairly large data sets. If I turn back to partial dependence plots, Dan's already demonstrated this. What I thought I would do is, though, mock up a little example of what happens in this particular case. This is the story for a single random forest. These are my calculation of individual conditional expectation and partial dependence plots. I've simply highlighted in the solid lines where there is a reasonable amount of data to support that ICE plot. These should be flat for x2, and x1 should be nicely linear, although you can see some attenuation. I tried using the ALEplot package, and you can see that attenuation. So these are the red plots, are the corresponding ALEplots. I was hoping this would be a more dramatic fix-up, I have to confess, but you can see that the attenuation has come back a little bit. So let me spend just a couple of minutes then saying, okay, so let's go a little bit deeper into what I would actually really like. If I'm looking at something like interventional feature attributions, and I say, basically, I need to recover additive components. The distinction between them, and I'm highlighting a new student coming out of Montreal here, who I've just become aware of, who's been writing about some of this. The distinction between them is really, what do you do with interactions, and specifically not what you do with the sort of interactional ALEPlots that Dan's very nicely produced, but what do you account for in interactions that you don't plot? That's easy to say in some contexts. If you look at ANOVA decompositions, you're really saying, I'm trying to minimize the size of those interactions. So I'm trying to capture things as well as I possibly can with additive models. There's other forms of things like anchored decompositions where you have a set of reference feature values where you're doing something very explicit about the interactions, or if you're looking at Shapley values, you're trying to apportion them. And so the question is, what does an ALEPlot do with an interaction? And if we want to say we're going to interpret these in some sense globally, how do they work collectively or how does the collection of ALEPlots function quantitatively as an approximation to the thing that you're trying to interpret? That is, how do I know that this is now a good representation or close to a complete representation of whatever interaction level I stop at of the object that I'd like. There's been a little bit of like ALEPlots work on little local effects. I would really, and part of the reason I'm pushing that is because I would really like to think of them globally, and I think that that's also largely the way that they're presented. And so having a quantitative here is a quality of the fit and how much we're capturing, and some guarantees about optimality about that would be really helpful. And that leads me also to a variable importance. Now, I suspect that some of this might be, those last couple of slides look like they're a fascinating set of answers to that coming out soon. But I will leave that with that and be happy to be told, well, we'll wait until the paper is published. But once again, congratulations to Apley and Ju. I think this is great work, and look forward to seeing it developed even more.
Thank you, Jill. Now I call on Qin-Yuan Zhao from Cambridge University as a second discussant.
Yes.
And then Daniel, if you want, you can reply after Qin-Yuan discussion. Okay.
Yes. Let me just find my slides. It's not on my screen. Can you all see my screen?
Yes.
Okay. Yeah. Thank you very much for giving me this chance to discuss this very interesting work by Apley and Ju. So I'm going to try to provide some causal perspectives on the ALEPlot, and I too acknowledge the research council that funds my research, and also Dr. Zijun Gao, who has been very helpful in our discussion about this paper. So first, I'd like to distinguish between two problems. One is the problem that's kind of described by Dan, which is about explaining a black box machine, maybe some random forest or neural networks learned from some data. So here I'm going to depart a little bit from Dan's notation. I'm going to call this f hat is some function that's learned from the data, but I'm going to treat that as fixed when I'm trying to explain this machine. I'm just going to stick with two inputs. So x is just x1 and x2. So the other problem, which is, I think, a lot of times, often what people actually care about is to explain the real world. So I'm going to let y be the original response variable used by the regression algorithm. And I'm going to talk about potential outcomes because I'm talking about causal perspectives on these. So I'm going to use a y bracket x1 to denote a potential outcome of the response variable under an intervention that sets x1 to little x1. I'm glad that Giles already mentioned this in his discussion I think this is really comes down to how you actually explain real world problems. So it may be helpful to think about, in this case, y is generated causally by some function of x1, x2, and some noise e. And in this case, you may define the potential outcome of y under this intervention of x1 by simply plugging in this value of little x1 in that equation. Okay, so I'm going to start with a causal perspective on the partial dependence plot. So as we have seen several times, this is the partial dependence plot proposed by Jerry Friedman. It basically takes the average of this function f hat at a fixed value of x1 and over the marginal distribution of x2. So in this previous paper I wrote with Trevor Hasty, we point out that this formula actually coincides with the confounder adjustment formula in causal inference, where this formula in causal inference tries to identify the average of the potential outcome of y under this intervention that sets x1 to little x1. So under some assumptions, you can equate that expected potential outcome with this formula that just takes the expectation of the conditional expectation of y given x1 is equal to little x1 and x2. So this is almost exactly the same as what the partial dependence plot does. Besides that, the partial dependence plot, you actually kind of know exactly what your conditional distribution of y hat given x1 and x2 is. I'd like to highlight that this formula is not free, right? So the left-hand side is about a causal quantity about some potential outcome under intervention, and the right-hand side are about quantities of the observed distribution. So this does require some additional assumption. So the most important assumption that you probably have heard about is this no unmeasured confounding or ignorability assumption that says the potential outcome of y under this intervention on x1 is indeed independent of x1 given x2. So there is a graphical condition that guarantees this called the backdoor criterion. And besides non-magic confounding or ignorability, you need some other assumptions like consistency and positivity to get this formula 1. So here I like to say ignorability is kind of automatically satisfied if your y hat, if the potential outcome of your black box prediction y hat is simply this function f hat evaluated at little x1. And second point is that I think this positivity and overlap problem is, what the ALEPlot tries to address, and we have already seen some discussion on that in Giles' comments. So I'm not going to go further into positivity, but what I will do is to try to give a causal explanation of what the ALEPlot tries to do. So the ALEPlot, I'm going to rewrite it slightly. That I'm just going to take a look at the derivative of this ALE function. So that's basically the expectation of the first partial derivative of f hat with respect to x1, and then averaged over distribution of x2 given x1 is equal to little x1. So I'm going to just look at the binary case. This is something that Dan hasn't described in detail, but in the binary case, Dan mentioned that this can be replaced by, the derivative can be replaced by a finite difference. So this is basically saying that your sort of f hat AO1 minus f hat AO0 is this conditional expectation. So this actually coincides with the formula for natural direct effect. So the natural direct effect is defined as follows. So I'm going to consider these two potential outcomes of y under an intervention that sets both x1 and x2, and their intervention that sets x1 and how that changes x2. So if I think about those as the potential outcomes under those interventions, then the natural direct effect is defined as follows. So it's the average difference between these two potential outcomes. So the first potential outcome is that you change x1 to 1, but you fix x2 at the value that it would obtain under, an intervention that sets x1 to 0. So this is almost like you go back in time, right? So you first change x1 to 1, but then when you're about to set the value of x2, you go back in time and change the value of x1 to 0. So you look at how that compares to sort of the potential outcome when x1 is set to 0. Then, so this case, so there's a well-known result in the causal inference literature that identifies this counterfactual quantity with this this quantity, which is almost the same if you compare it term by term. This is basically the same as the ALEPlot, the first term in the ALEPlot. This is the same as the second term in the ALEPlot. And then you take the same sort of conditional expectation given x1 equal to 0. So what I gather from this observation is that basically what ALEPlot tries to do, perhaps sort of intuitively or even subconsciously, was to find these kind of accumulated local natural direct effect. Again, for this result to hold, it is not, well, it requires some additional identification assumption. So for this equality to hold, right, because the left-hand side, again, is a counterfactual quantity, the right-hand side is a quantity from the observed data distribution, we do need some assumptions. The main assumptions are these three kind of no confounding assumption between the treatment and mediator, the treatment and the outcome, and the mediator and the outcome. So the last two assumptions would be automatically satisfied if I'm looking at this kind of black box interpretation scenario. So in that case, my potential outcome of y hat is simply this function f hat evaluated at this point. So there's no randomness in this potential outcome. So these conditional independencies would automatically hold. But the first assumption is about sort of no confounding between x1 and x2, and that may or may not be true. So it may be useful to sort of understand this from a graphical perspective. So what graphs does these causal interpretations need to assume? So if I consider these mixed graphs with directed and bidirected edges, where the directed edges means direct causal influence and bidirected edge means exogenous correlation, then what happens is that for the partial dependence plot to be valid, then you need sort of x2 to control for all the confounding between x1 and y hat. So these are three graphs where this no confounding assumption is true for the partial dependence plot. So when that is true, you identify the average treatment effect, essentially, of x1 on y hat. So for the ALEPlot, it is valid when you basically, either in this case where x1 and x2 are independent, or in the second case where x1 affects y hat partially through this mediator x2. And in these two cases, the ALEPlot would identify the natural direct effect of x1 on y hat, so the effect along this sort of directed edge. I don't have a lot of time left, so maybe I'll just go through one more example, and just to say, so far I've tried to say, well, the partial dependence plot and ALEPlot have causal interpretations, but I'd like to sort of put forward an even stronger case and say, well, when we are explaining these black box algorithms or explaining real world phenomena, it does need to be, I think, causal for these explanations to actually be very meaningful. And this is a very sort of simple example to try to suggest that. So here, let's say we have two ID random marker random variables, W1 and W2. So they take the values 1 or -1 with half probability. So let's consider my first y hat, which is a function of W1 and W2, but it's actually just equal to W2. So this is very similar to an example Giles showed. So in this case, you would certainly think that the explainability of W1 to y hat should be 0, because of course, I mean, y hat doesn't depend on W1, isn't it? Okay, so that's very natural, but let's consider alternative scenario where, let's say I know my W2 is actually generated from this equation that is actually equal to W1 times another independent Rademacher random variable W2 prime. So W2 is just a product of two random signs, and one of that random sign is W1. So then when you plug that in to my equation, so I can write y hat as a function of W1 and W2 prime, and that's just a product of them, then surely in this case, you would probably think the explainability of W1 to y hat should be non-zero, because obviously y hat depends on W1. So what's sort of paradoxical here is that, I mean, I've actually, the y hat as a random variable are the same, right? So W2 and W1, W2 prime are exactly the same. They're the same with probability 1. But why would the explainability of W1 to y hat be different in these two scenarios? So I think this paradox really arises because the same variable, well, the same variable y hat doesn't mean they have the same potential outcomes. So in the first case, what we're actually thinking by writing that down as a function of W1, W2 is that the potential outcome of y hat of W1 is always equal to W2. And in the second case, that potential outcome is actually different. It's W1 times W2 prime. So I think this is something that's a bit difficult to get if you're just completely coming from a probabilistic or prediction kind of perspective. If this sort of notion of potential outcomes is not natural to you, then this is a bit probably a bit difficult to interpret or understand initially. But really, I think this shows that really we need to think about explanations in a causal way. I'm going to skip this example and just say my take-home messages are: first, PD and ALEPlots have causal interpretations, but these causal interpretations do require additional assumptions about the causal relationship between the predictors. And it is my personal belief that explanations of black box machines are really meaningful only when these explanations are causal. Thank you very much for letting me discuss this really interesting work. Yeah, thank you.
Thank you very much to both of the discussants. And now I think that Daniel might like to rejoin there somehow.
Okay, sure. Yeah, thank you guys. Really interesting comments. As of, I don't know, 2 weeks ago, I hadn't thought about causality at all. But I think I mentioned earlier, my PhD student just defended a week and a half ago, and one of her committee members does quantitative marketing and, really thinks about causality a lot and brought up that, some of the same issues. I still don't really have an answer to it. I guess the answer is ALEPlots interpret the fitted model as it is in all its stupidity. The fitted model doesn't understand causality issues. It just interprets the way the numerically, mathematically, the variables involved in F impact the function F itself. No regard to causality. I have to think about this a lot more. I think it's a really interesting area to, bring in causality considerations into things like this. I don't know. I guess you guys know a lot more than me, but I was thinking that would be a problem not so much with ALEPlots, but with just the F itself, the model specification, where if you could, when you're fitting F, if you fit, I don't know, Bayesian network or whatever, kind of incorporate those causality issues into the model itself, F, then maybe applying ALEPlots or something like that with some modifications could produce correct causality interpretations. Yeah, I guess my understanding is that what ALEPlots really tell you is what I think is called the direct effects in the causality literature. Direct effect of the variables, where if you got a data set with x1 and x2, and y is equal to x2, but x1, no direct dependence on x1 given x2, but x1 causally affects x2, then just mathematically in the model, when you fit a regression model with both x1 and x2, with enough data, x1 won't appear at all. So mathematically, x1 doesn't affect f, and that's essentially what the ALEPlots would tell you. So maybe, yeah, the committee member I mentioned even made a comment where, produces nonsense or not useful. I think it's still useful, but you just have to understand what it's telling you. It's helping you interpret how the variables impact this model that you fit. It's not telling you in reality, if you have the interventional setting, if you break the correlation between predictors in a but-for situation, it's not telling you what you could expect then. It's just literally telling you what f thinks it's spitting out as a function of your x's, which I think is still useful as long as you understand that it's missing all these important causality issues that you guys have raised.
Okay, so there is a question in the chat that is somehow related, I think, to something that also Gilles mentioned, and it is how do your plots relate or compare to Shapley values and plots?
The Shapley values, the numerical values, I mean, that's different. This is not spitting out a numerical importance measure, doing a plot. As I mentioned, we do have a paper we're about to submit that did some basically a variable importance version of ALEPlots, and we compared them extensively to Shapley values. Theoretically, there's some differences. Numerically, we found it was sort of the same thing. Shapley values, at least most of the implementations, require some extrapolation too. And what we found was similar to PD plots, where numerically, if the data was more well-behaved, less extreme correlation, our results usually agreed, at least in terms of the relative ranking of the variables, pretty close with Shapley. We found ours were less variable across replicates, sort of more reliable though in situations when correlation was high. Yeah, and then the Shapley plots, if I understand, I think they're just showing kind of locally how small changes affect the predicted response on average. Does it increase? And I don't think they show interactions, right? They only show, unless there's a version of Shapley plots that actually show the interaction effects too. I'm not sure about that.
Okay, thank you. One more question from the audience. Joshua Loftus. You can switch your microphone on. I see your hand raised. Okay, so Paolo Giudici. Paolo, you can turn your microphone. Okay, thank you. Good.
Yes. Good afternoon, and thank you for a very brilliant and very interesting talk. I have a couple of questions or remarks. I myself work in the area of explainability and trying to understand in the black box. So first question I have is also about Shapley values. I don't want to go into details of Shapley values, but a key advantage of Shapley values is that they measure the effect of that specific variable in all combinations, all possible combinations with the other, so that clearly can take interaction effects somehow into account. Furthermore, Shapley values, actually with the sharp version of Shapley value, you don't need to retrain your model, which is a clear advantage when you work, for example, with large language models. So I think that these two aspects should be captured also by your method. No? So that is one question. If you are able to do your say apply your explainability model without the need to retrain the model. Other two questions relate to other characteristics that one may expect from explainability. That is the need for the explanations to be robust, no? So not to change, when you vary the sample or even for small variations in the sample. That is the issue of robustness of explanations, which is very well known in the machine learning field. So I was wondering what you can say about the robustness of your method. And last, about, let's say, the concentration of the explanations, because, very often we have so many, in real problems, we have so many variables at hand that one may want not only good explanations, but parsimonious explanations, that a few variables explain most of the story. So I was wondering also what you can say with your method about concentration explanations. Thank you.
Yeah, thank you for the questions. I'm not sure I remember all of them. Maybe you can remind me some of them. But for robustness issue, I think a lot of the lack of robustness is just due to having to extrapolate. And again, at least the SHAP version of Shapley effects has to extrapolate. Something I didn't talk about but alluded to, the variable importance measures that we're developing for ALEPlots. If you want to measure just main effect importance, that's kind of a no-brainer with ALEPlots. If you like ALEPlots and believe it's producing something meaningful, you just take the variance of the main effect ALEPlot function that gives you a main effect importance. You can do the same thing for the interaction plots. If you want to find the total importance of a variable, including only up to second order interactions, you could maybe take the variance of its main effect plus all interactions, AL interactions that involve that variable, and look at that. That would, of course, double count across variables some importance, but that's what a lot of global sensitivity measures do. Then what we've developed, and those are kind of almost trivial ways to get VIMs out of ALEPlots. What we were working on is something that will do a total effect importance that will implicitly consider interactions of all orders without having to actually compute them. That's what we had compared to Shapley effects and found it to be, robust is kind of a broad word, but at least robust to having correlated data and doing multiple replicates, and we found more consistent from replicate to replicate. Parsimonious explanations, I guess maybe the best way to get parsimony, when you're fitting them on, if F itself you considered parsimony, use some sparsity regularization when you fit F and dropped a lot of variables out, then that's maybe the best way to get parsimonious representations. I guess if you didn't do that and included all the variables, my favorite way of getting some parsimony and explanations is just to use some variable importance measure, whether it's Shapley or what we're trying to develop, rank all the variables and get rid of take only the top so many percent and then try to interpret them. I don't really know how else to get accurate but parsimonious interpretations. And then I think you had mentioned something about applying to large language models.
Yes.
That's about one situation. Large language models, convolutional neural network, image processing, that's why I don't think the ALEPlots are very relevant. Because you've got so many, such high dimensional variables, and so the variables themselves, pixels in an image, aren't that reasonable or aren't that meaningful to interpret the effects of. The only thing I've really thought of where you could apply ALEPlots for complex models like that, let's say it's a convolutional neural network with many, many layers. You got the last fully connected layer, and the inputs to that layer you can view as features that were extracted from the image. Maybe you would apply ALEPlots with the X's replaced by the features in the output by the second to last layer. And then, assuming those features were kind of meaningful, you could at least interpret their effect on the response. But that's kind of trying to engineer an ALEPlot solution where I'm not sure ALEPlot would be the best solution for models like that. Is really when we developed it, it was intended more for the, tabular data where you've got a set of 10, 20, 30 well-defined X's.
Yes.
Okay.
I don't know if the other folks have any thoughts on that.
Well, I am sorry to interrupt this very interesting discussion, but I have been reminded that it's my task to keep the time, and we are running a little bit out of time. So I would like to thank all the speakers of today for this interesting and really insightful talk. And I would like to remind you all that the next journal webinar will be in a week, next Monday, same time, 4 p.m. British time. And the paper which is going to be presented is a Series A paper by Hancock and Adrian Raftery titled Model-Based Clustering for Social Networks. So thank you very much to you all for attending, and to the speakers for the very, very nice afternoon we have had the chance to spend together.
And
So
thank you,
bye-bye.
everyone.
Thank you.
Bye-bye.
I've got to
Thank
think
you.
more about that causality stuff. I'm going to spend the next week thinking about that.
Okay. Bye-bye.
Bye-bye.
Bye-bye.